In this video, we will talk about velocity and acceleration of particles. So we are talking about physical objects idealized as rigid bodies, and they have no size and shape. They are being modeled as particles where all of their mass is concentrated. So we'll start with our basic translation motion. Okay, so we'll talk about first translation and then we'll discuss rotation. So let's say I have an object, and remember now its size and shape is not important. I show it as a square or a rectangle over here, but that's not important. I could have just drawn it as a particle as well. Let's say initially it's over here, and after delta t amount of time it has moved, let's say by delta x distance. Okay, so it has moved in delta t amount of time from point P to, let's say, point P prime. Okay, and it does have some mass. So if it has moved by a certain distance over a certain amount of time, we can give rise to something called an average velocity. We'll call it V average, defined as the distance traveled divided by the time it took for it to travel, right? And that's sort of your measure of an average velocity as this particle moves over a certain distance. However, this kind of measure is actually not very useful. So if you have ever driven a car or any other vehicle, you can actually read your speed at any given instant. So we are more interested in what is the velocity or the speed at a particular instant, which we call instantaneous velocity. So if I want to find out what the velocity of this particle is at, let's say, at point P, then I have to make this time period very, very small. So I have to essentially bring P prime as close as possible to the P, which we can do if I take limit delta t going to 0. Okay, so in the limit when delta t goes to 0, what is this quantity? In calculus, you learn that this quantity is defined as v. Okay, now this itself becomes dx over dt. So that's the differentiation of x with time. So the velocity is nothing but dx over dt. You can ignore this vector sign over here for the time being because we are only talking about a straight line, only one direction. Okay, so that's your basic definition of the velocity. You differentiate x with respect to time. If you know x as a function of time, you can get that. Similarly, we can define what we call an average acceleration. So average acceleration would be defined as the change in velocity over time. So let's say velocity over here was v, and here it became v plus delta v, then the change in velocity is v plus delta v minus v, which is equal to delta v, and that gives rise to average acceleration. Again, it's not very useful. We are interested in instantaneous acceleration, so we will take this in limit when delta t goes to 0, and that would be equal to dv over dt. So the definition of the acceleration is dv over dt. So if you know velocity is a function of time, you can also determine what the acceleration would be. Okay, and these are fairly simple concepts. Now, all this applies even if a particle is not moving along a straight line path. So for example, if let's say I have a particle moving along a curved path, okay, I'm going to pick my coordinate system. Now in this case, instead of x and delta x, I would have, let's say, position vector r, and that's at time instant t, and then after a while, let's say this is a time t plus delta t, so the elapsed time is delta t going from P to P prime. The position vector is r prime. Okay, now this vector over here, let me draw it with a different color. This vector over here is the difference between r prime and r, right? Because if let's say this is delta r, then I can write delta r plus r equal to r prime. Right? In other words, delta r is nothing but r prime minus r. Okay, so that's the differential distance traveled. So delta r over here is perfectly equivalent to delta x over here. Okay, so if you want to define the velocity, it would be defined in an analogous fashion. It will be defined as limit delta t going to 0. So when the time interval is very small, distance traveled over time. Now, instead of this being delta x, this is actually a differential vector. So what is this quantity? This is equal to nothing but dr over dt. So that's a differentiation of r with respect to time. And if you extend this further, you also get acceleration as dv over dt. So those are your fundamental relationships that we will be using to find velocity and acceleration in this particular video. Okay, all right, so that's good. Now let's look at some of the specific cases. So there is a case when you have what we call uniform motion. So uniform motion is defined by the fact that velocity is constant. So if a particle is moving with constant velocity, what happens? So let's see that. So v is equal to dx over dt, and this is constant, so we'll write this as v0. So I can write this as v0 times dt, and I can integrate both sides, right? Now you guys know how to do integration. v0 is a constant, so I can take it outside. This becomes integral dt, and integral dx would be basically from some x0 to some final x. Okay, so that's a definite integral. So what do we have on the left hand side? Well, this is integral dx, so that will be x. So that's x minus x0 equal to v0 times the distance, the time elapsed, right? So that's, let's say, I will call it delta t. So that's delta t. So we get x equal to x0 plus v0 times delta t. So that's the formula that you get when you have uniform motion, or in other words, when velocity is constant. So you can use this formula only when the velocity is constant. So let's do an example. So let's say I say that there is a particle, okay, and it's initially at x equal to 0, all right, and it is moving with constant velocity v0 equal to 5 meters per second. The question is, what is its new position in time t equal to 2 seconds? Okay, so let's say that's the question. So all we have to do is, in this case, because we know that this is given as constant velocity, so this is a constant velocity, we can find x equal to x0 is 0. So let me write this formula again. x0 is 0 because initial position is given as 0. v0 is given as 5. Delta t is given as 2. So x would be equal to 10 meters. That's its new position. Okay, so x is equal to 10 meters. That's the answer. Now this question could have been phrased in a different way as well. So the question could be that I know my initial position. So let's say I will rephrase this question slightly differently. Initial position is 2 meters. The final position is 5 meters. Okay, and it has gone from 2 meters to 5 meters from this position P1 to P2 in, let's say, 5 seconds. And assuming that this particle is moving at uniform velocity or at constant velocity, the question is, can you find that constant velocity? So if it is constant velocity, so we can again use this formula. So x equal to x0 plus v0 times delta t. Final x is 5, initial x is 2, plus v0 is an unknown, delta t is 5 seconds. So we get v0 equal to 3 over 5 meters per second, which is 0.6 meters per second. However, keep in mind that this formula is valid only if velocity is constant, and that's given to you. If you don't know velocity is constant, then don't make that assumption. So this is what we call uniform motion. A second kind of motion that's very common is what we call uniform acceleration method. Acceleration motion, not method, uniform acceleration motion. So what's uniform acceleration motion? In uniform acceleration, acceleration is constant, not the velocity, but the acceleration is constant. Let's say that's a0, okay? So we know the definition of acceleration. Definition of acceleration is dv over dt. We'll start with the definition of the acceleration, and that is a constant a0, okay? So just because that's constant, you will see things become very, very simple. So I'll take dt on the other side, and remember, whenever you're doing these kinds of integrations, you have to have no more than 2 variables, okay? So in this case, the variable is v and the t, okay? Acceleration is no longer a variable because that's given as constant. Now let's integrate it. So initial velocity being v0, final velocity being v, and a0 is a constant, so it's going to come out. So I'll write it as a0 times dt, and that's integral from 0 to delta t, okay? So we're assuming the initial time is 0. It doesn't have to be. It could be some other number as well. So this gives us v minus v0 equal to a0 times delta t. So v is equal to v0 plus a0 times delta t. And I'm pretty sure that you guys have seen this equation in your high school physics classes, which is one of the Galileo's equation, right? So If acceleration was given to you as constant, then you could use this equation to relate the final velocity with the initial velocity with the acceleration and the time elapsed. But I'm sure you have seen some other forms of this formula as well, wherein you don't have velocity, but you have actually the distance traveled, or you have the distance traveled related with the acceleration with no time in there, right? So how do we get all those equations? Let's first write the definition of the velocity, which is given as ds over dt. Okay, so let's say we will call it ds over dt. We have before you use dx over dt, doesn't really matter what symbol you use. So s over here is perfectly equivalent to x that we used before. Now let's look at our original acceleration formula, which is this. So the original acceleration formula is that acceleration is dv over dt. Okay, so I'm going to integrate this. So I'll bring dv on this side and I'll put a dt on this side, and acceleration is constant. This will be a0. So let's integrate it from initial velocity v0 to v, and this is equal to a0 integral dt, and that's from 0 to some time t. Notice I'm not substituting delta t over here because t is actually a variable that I want to retain here. So this will be a0t, and this will be v minus v0 equal to a0t. So v itself is ds over dt, so I'll write that, and v0 goes on the right side, so this will be v0 plus a0t. Now I can integrate it one more time, so v0 plus a0t times dt, integrated from some initial s0 to some final s, and this changing from 0 to now we can substitute delta t if we wanted to. Okay, so this will be s minus s0 equal to v0 times t, which is delta t, plus 1/2 a0 times delta t square. So we get s equal to s0 plus v0 delta t plus 1/2 a0 times delta t square, and that's the distance traveled. So if you were trying to relate the acceleration with the initial velocity, time, and the distance traveled, you can do that via this particular equation, and that's your other form of Galileo's equation. Now there's one more equation that you have seen where there is no time involved. How do we get that? So we again go back to our original definition of acceleration, which is dv over dt, and that is equal to some constant acceleration. Now dv over dt, we'll do a little change of variable here. We'll write it as dv over ds times ds over dt equal to a0, and that's perfectly acceptable. Now what is ds over dt? ds over dt is nothing but the velocity. So what we're getting is v times dv over ds. Notice I wrote v first equal to a0. Now we got rid of the time from this. So we'll keep v dv on this side, and we will bring ds on the other side. So remember, the trick to doing the integration like these is that you keep all one kind of variable on one side and all the other kind of variable on the other side. So on the left hand side we have all the velocity variable, on the right hand side we have all the distance variable. Acceleration is constant. So now integrate this, initial velocity being v0 to some final velocity, initial distance being s0 to some final distance. So we get v squared over 2 changing from v0 to v equal to a0 times s changing from s0 to s. Remember, these are all definite integrals. So we get v squared minus v0 squared over 2 equal to a0 times s minus s0. So by the way, s minus s0 is nothing but the final position minus initial position. So that's also the total distance traveled. So we get v squared equal to v0 squared plus 2a0 s minus s0. And that's your third equation from Galileo. So you can see that Galileo's equation, there's nothing special about them. They all come about from this basic definition when acceleration is assumed to be constant. So keep in mind that you cannot use Galileo's equation unless acceleration is constant. So let me write this. Do not use these equations unless acceleration is constant. Okay, so if acceleration is not constant, you can't use these equations. So for example, if let's say something is falling freely, and falling freely means, you know, falling only under the influence of gravitational attraction. So let's say there's some particle that's falling freely under the acceleration g only, assuming that this is falling through a range where acceleration due to gravity can be assumed to be constant, then g is actually constant, which is 9.8 meters per second squared in USCS system, and is equal to 32.2 feet per second squared in USCS system. sorry, 9.8 meters per second squared in SI system, and this will be in USCS system. So in this case, acceleration is constant, so you can use one of the Galileo's equation. On the other hand, if I said that also consider the effect of air resistance. So if you consider the effect of air resistance, then its acceleration, in fact, when it is falling downward, if you consider the air resistance, then there will be a deceleration, and that deceleration would actually not be constant, because it would depend on the velocity with which it is falling. And that's the same condition if, let's say, this was falling through liquid, let's say, water or something fluid like that. So if acceleration is not constant, you can't use Galileo's equation. So keep that in mind.